Picture this. You've got a massive, state-of-the-art manufacturing facility, and it is just humming along perfectly. It's powered by this lightning-fast private 5G network, and the whole operation is guarded by literally the most advanced artificial intelligence security systems money can buy. But then, out of nowhere, the alarms start blaring. The AI is practically screaming, flagging massive, critical cyber attacks. So the security team scrambles, they lock things down, they investigate, and they find absolutely nothing. The factory is totally fine, it's perfectly safe. So you have to wonder, what is going on here? Why are these top-tier AI security systems suddenly seeing ghosts in the machine? Well, welcome to The Explainer. Today, we're diving deep into this exact mystery to figure out why these false alarms are crippling industrial 5G networks, and more importantly, how we can actually fix it. Let's get into it.
To unravel this whole thing, we really have to ask ourselves a pretty provocative question. Is it actually possible that completely normal, routine network hiccups are somehow disguising themselves as malicious cyber attacks? Like, could a slight, everyday connectivity wobble actually look like a sophisticated hacker to an advanced artificial intelligence? Well, to understand how that could even happen, we need to quickly look at the specific type of security system we're dealing with here.
In these modern smart factories, the security heavily relies on an MLIDS. That's a machine learning intrusion detection system. Now, the absolutely defining constraint for these systems is encryption. Because modern industrial networks use the OPC UA communication protocol with a heavy-duty security mode called sign and encrypt, the AI literally cannot read the actual data payloads. It's locked out of the contents. So instead of reading the data, it has to rely entirely on observing traffic behaviors, things like packet patterns, data volumes, and timing, to try and guess if something malicious is happening.
Now, on the surface, this heavily encrypted environment sounds like an absolute cybersecurity dream, right? I mean, you've got industrial private 5G networks ensuring really rapid, isolated communication. You've got the OPC UA protocol organizing everything. And it's all locked down incredibly tight with that sign-in encrypt protection. Nobody is getting in and reading that data. But here is the fatal flaw this creates for our AI security guards. It completely forces what we call payload-agnostic monitoring. The AI is blind. It can only watch the shadows that the data casts on the network walls. And as we're about to see, those shadows can be incredibly deceiving.
The root of this whole ghost story actually starts with how these AI models are trained in the first place. You see, they are typically trained in pristine, perfectly controlled lab environments. In a lab baseline, the network is flawless. Devices connect instantly, they stay connected forever, and the data just flows perfectly smoothly. But you know as well as I do, real-world private 5G deployments are messy. They're chaotic. A giant metal forklift drives past a sensor and blocks the signal. A heavy machine is powered down for routine maintenance, or a mobile device just naturally needs to refresh its connection. The real world is packed full of completely normal, non-malicious connectivity variations.
Well, let's actually break down exactly what those routine variations look like, because in a real 5G network, these benign events are happening every single day. The researchers specifically mapped out 4 common scenarios. First up, you have what's called a hard UE reconnection. This is basically where a user equipment device drops off the network entirely, and it has to do a full registration, reestablish its security, and recover its data session from scratch. Second, there's a soft UE reconnection, which is a bit smoother. It's a graceful deregistration followed by a re-registration and session reestablishment. Third, we have a PDU session reset. This happens when the actual data pipeline itself releases and reestablishes, which causes a brief, transient disruption in the user plane traffic. And finally, the fourth scenario is a PDU session interruption. This is just a temporary pause in user data that triggers what are known as connection management state transitions. Now, here is the absolute most crucial takeaway from all of this. Every single one of these expected effects, the registrations, the session recoveries, the state transitions, they are 100% harmless. There are no malicious hackers here. It's just the normal, everyday physics of running a wireless network.
Okay, so we've established that these hiccups are totally normal, but the million-dollar question becomes, what actually happens to the data when we test these completely benign scenarios against those state-of-the-art AI security systems? Do the models recognize them as normal and just shrug them off, or do they completely misinterpret them and sound the alarm?
To find out exactly how the AI reacts, researchers evaluated 4 of the absolute top supervised machine learning models currently being used for this exact type of network monitoring. We're talking about the heavy hitters here. They tested logistic regression, random forests, support vector machines, and extreme gradient boosting, which is usually just called XGBoost. Now, keep in mind, these models were rigorously trained.
They are supposed to be the best of the best at pattern recognition, explicitly designed to distinguish between safe baseline OPC UA traffic and actual malicious cyber attacks. So let's really dive into the data and analyze the impact of these harmless hiccups, because the results are pretty shocking. When we chart out the performance of these 4 models, we can clearly compare their baseline performance against how they act during a network variation. In a pristine baseline state, represented by the solid white bars on the chart, all 4 models sit comfortably with a false positive rate between roughly 3.5 to 4.8%. Honestly, that's totally acceptable for a baseline. But look what happens when you introduce those benign connectivity variations we just outlined. The striped bars on the chart show a massive spike. The false positive rate effectively doubles across the entire board. Logistic regression jumps from 3.53% all the way to 8.02%. Random forest goes from 4.71% to 8.61%. Support vector machines hit an incredible 9.15%, and XGBoost surges from a totally manageable 4.12% up to over 9%. The fact that this dramatic doubling happens across 4 completely different mathematical models tells us something incredibly important. This isn't just a single glitchy algorithm, it's a systematic failure. The models aren't broken, they are all being universally tricked by the normal behavior of the network itself. Let's just focus on that XGBoost number for a second. 9.02%. Think about what a near 10% false positive rate actually means in the real world. In a massive industrial facility that's processing millions of network packets every single minute, a 9% error rate translates to constant blaring alarms. It means severe alert fatigue for the security team, which is incredibly dangerous, because if they get used to ignoring false alarms, they might just ignore a real cyber attack when it finally happens. The AI is systematically flagging completely safe, normal factory traffic as a critical cyber event.
Alright, so we know for a fact that the AI is getting confused. But to actually solve this mystery, we need to know the specific trigger. When exactly are these false alarms happening? Can we trace a direct temporal link, like a perfect timeline, between those normal network hiccups and the exact millisecond the AI decides to have a panic attack? When the researchers mapped out this timeline, the resulting visual is nothing short of a smoking gun. Let's break down exactly what the data visualization reveals across these benign scenarios. Imagine a graph where you have a dashed horizontal line that represents the AI's decision threshold. If the system stress level crosses that line, the alarm sounds. Now, tracking along that graph is a solid black line representing the AI's real-time anomaly score. The researchers then mapped out periods of control plane activity, which are the exact seconds the network is handling routine background maintenance like a device registration or a session reset. They highlighted these specific maintenance windows with light blue vertical shading. When you layer all this together, the relationship is undeniable. Literally, exactly during those blue-shaded maintenance periods, that solid black anomaly line violently spikes right up over the dash threshold. It's perfectly correlated. The encrypted data patterns naturally shift for a split second during these device reconnections, and the blind AI instantly predictably assumes it's under attack. The AI isn't just randomly failing at all, it's failing the exact second the control plane kicks in to do its job. So, we've definitively found our culprit. The smoking gun here is the control plane activity. The research completely proves that lightweight, background control plane indicators, things like basic registration events and routine connection management state transitions, are directly responsible for tricking the user plane AI detection system. Basically, the AI is intensely watching the user data lane. It sees a sudden weird pause or a burst simply because the network lane is doing some background maintenance, and it completely panics.
Let's use an analogy to make this absolutely crystal clear. Imagine our AI is a human security guard stationed inside a highly secure, completely windowless building. Suddenly, the fire alarms start going off, the elevators lock down, and the heavy blast doors slam shut. The guard obviously assumes the building is under some massive, coordinated attack and immediately calls in the SWAT team. But, in reality, the building management was just running a routine, scheduled fire drill. The guard panicked simply because no one bothered to hand them the testing schedule. Our AI is exactly like that isolated guard. It completely lacks the context of what the network management is actually doing in the background.
So how do we fix it? Well, network engineers need to extract specific, lightweight control plane indicators to finally give the AI that missing context. The AI desperately needs to be informed about 4 key things: registration events, connection management state transitions, PDU session state changes, and resource reconfigurations. By pulling these specific indicators straight out of the non-access stratum and next-generation application protocol messages in the 5G network, we can basically whisper in the AI's ear and say, hey, listen, the data's about to look a little weird for the next 3 seconds, but don't freak out, it's literally just a soft device reconnection.
The researchers really hit the nail on the head here when they summed up the solution in their conclusion. They explicitly state, future work will investigate control plane-aware intrusion detection approaches that combine encrypted traffic features with CP context information to improve robustness. That right there is the absolute future of industrial 5G security. We can't just stare blindly at encrypted data patterns anymore. We have to build control plane-aware systems that are simultaneously looking at the network context.
Which really leaves us with this final critical thought. As we constantly rush to deploy more and more advanced AI to protect our most vital industrial infrastructure, we really have to stop and ask, is your AI security system actually seeing the whole picture? Or is it isolated in the dark, jumping at shadows in the network? Because context isn't just some nice-to-have bonus feature in cybersecurity anymore. As we've clearly seen today, it is literally the fundamental difference between a truly secure network and an endless, exhausting stream of false alarms. Thanks so much for joining me on this explainer, and as always, keep questioning the data.